Back. Today we're going to prove some of the characterizing properties of the exponential function and the trig functions sine and cosine. Remember, we're dealing with these complex power series definitions of the exponential function and the cosine function and the sine function. And this is likely to cause some worry. Are these really the exponential function, the cosine function, and the sine function, or are these just some power series that my professor made up? So to try to answer that question, we're going to prove some basic properties of these series, but keep in mind that we've already proven a lot of basic properties of the exponential function. We're going to rely on those a bit. And then we're going to prove that basically any other function that satisfies those properties must be equal to these functions. And so we're going to link them with our prior knowledge about sine and cosine and e to the x. So to begin, what are we going to prove? First of all, e to the z is never zero. This is obvious from exponentiation, but is not obvious from the power series definition. It's perfectly reasonable to expect there might be z values that you would plug in here and get zero. The proof of 1 is very straightforward if you remember the key property from last time, which is that e to the w times e to the z is equal to e to the w plus z. So if we let w and z be opposites of each other, then e to the minus z times e to the z is equal to e to the 0, which is equal to 1. And this proves that e to the z always has an available reciprocal, namely e to the minus z, and I suppose if it has a reciprocal, then it can't be 0. So that establishes that e to the z is not 0. So that's our proof of 1. Next, we're going to prove a basic property of e to the z, but actually we're going to make a slightly more general property, e to the kz, and we're going to demonstrate that its derivative is just what you expect. I'm not going to prove this. This is just a simple application of the chain rule. We've already proven that the derivative of e to the z is e to the z, and remember, what we did was we just differentiated this term by term and saw that we just got e to the z when we differentiate. So if we just apply the chain rule to that fact, then we get that the derivative of e to the kz is ke to the kz. This means that e to the kz is a very special function. It's proportional to its own derivative, and the constant of proportionality is k. Now, there aren't a lot of functions that can do that, and that's the point of this third claim here. If you have a function which is proportional to its own derivative, if f prime of z is equal to k f of z, so that f prime of z is over f of z is equal to k for all z, then that function is just a constant multiple of this key function e to the kz. So in other words, every function which is equal to k times, every function whose derivative is k times the function is a multiple of this one, which has the same behavior. That's a kind of a uniqueness property, and it reassures us that there's really only one way for a function to be proportional to its derivative. So how are we going to prove 3? All we need to do is show that there is essentially only one type of function that can do this. So here, let's let f prime of z be equal to k f of z. And similarly, let's let g of z be the other function that does that, namely e to the kz. So that g prime of z is also k g of z. So now we have potentially two functions that behave in this way, that their derivative is k times their value. Now, let's consider, I want to take the ratio between them. Now, the reason I did part 1 here is because up front, I don't know that the denominator of this function, f over g, is going to be non-zero. But if I know that e to the z is never 0, then I know that g of z is a non-zero function. So let's take the ratio between these functions, f of z over g of z, which I know is always defined because the denominator can't be 0, and let's just differentiate it. So if we differentiate this function by the quotient rule, then we'll get, what will we get? F prime of z, g of z, minus f of z, g prime of z, over g prime over g squared. So g of z quantity squared. And so f prime is kf, and g prime is kg. And so this is kfg minus kfg, which is 0. And so that means that f of z over g of z is constant. And that means that f is some constant multiple of the exponential function e to the kz, and that's exactly what we're trying to show. So in other words, if the derivative of a function is a constant multiple of that function, then that function must be the exponential function. And this is a key uniqueness property. And it means, so notice that this proof works if it is a complex proof. This proof works, and all of these proofs work if they are complex proofs. They work if they're real proofs. And that means that if you already buy into a real valued function e to the x, and you already believe that that function is equal to its own derivative, then, but if perhaps you don't believe that it's equal to this power series because you haven't seen the power series before, or if you have other doubts, then what this establishes is that your function e to the x that from your prior learning and my function e to the z, which can be restricted to the real values, well, they at least share the property that each one is equal to its own derivative. They at least share that they both have this property for k equals 1. And if they both have this property for, then what part 3 asserts is that one is a constant multiple of the other. And that means that your prior knowledge function e to the x and my power series function e to the z are actually only off by a constant multiple. And it's easy to figure out what that constant multiple would be, because when we evaluate them at 0, we both get 1. And so that constant multiple must be 1. And that means, of course, that those functions must be the same, at least for the real inputs on which they're both defined. And so this reassures us that, even if you didn't believe that e to the x has this power series, even if you didn't believe that that looked like a correct definition of e to the z, it does obey enough properties that it must be equal to the original function e to the x from prior knowledge, at least for real values of x. All right, what we're going to do then is we're going to prove 4 and 5 next, and these are going to establish similar properties for the sine and cosine functions. What I'm doing is I'm proving that sine and cosine, according to these definitions, obey some basic properties that should be familiar from your prior knowledge of sine and cosine, and then I'll prove a uniqueness property that says if any function, and that's stated here in 5, if any function obeys just these properties, then it must be equal to the sine and cosine functions that we've defined here. And therefore, well, then if you have some prior knowledge of functions called sine and cosine from high school trigonometry, and if you believe that these things are true of sine and cosine from high school trigonometry, then your sine and cosine functions restricted to the real numbers must agree with my power series applied to the real number inputs. And so that will sort of link in the development of the new sine and cosine with the prior knowledge of sine and cosine. So let's get started on 4. 4 is fairly simple, and I'm not going to go into details. I'm just going to sort of gesture at how that's supposed to be done. So 4 is about the cosine and sine as defined in these power series. In 4a, we assert 2 derivative properties, and they're quite simple. Notice that we've already proven that these things have infinite radius of convergence, and we've already proven that the formal derivative of a power series with infinite radius of convergence calculates its actual derivative. And so that means that if we want to differentiate sine, then we can go into these terms and we can differentiate each term. If we differentiate z, we get 1, z cubed over 3, over 3 factorial, its derivative is z squared over 2, z to the 5th over 5 factorial, its derivative is here, and so on. The signs all match up, so we differentiate this term by term, we get cosine. And similarly, you can check that when you take the derivative of cosine term by term, this z squared over 2 becomes minus z, and so I've actually dropped a sign here, so let me correct that. So this is supposed to be minus sine z, and I copied it here, so sorry about that. So when we differentiate cosine, we get minus sine, as is the usual formula. Now, so that's just term-by-term differentiation. So I'm going to declare a, so the feature that sine prime of z equals cos of z, and that cos prime of z equals minus sine z, we're going to call that good. But what about this, this claim here? This claim here is really sort of a double claim. I'm claiming that sine squared z plus cos squared z is constant. That's not easy to see from the expansion of the power series. You could imagine multiplying out these power series and squaring this one and squaring this one and trying to combine terms. That's not easy to see. I'm also claiming that it follows immediately from this, right? So dot 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 so that's sort of suggesting that it follows immediately from this. And that's what I'm actually going to do. I'm going to deduce it immediately from this without any other use of the power series. So all we have to do is take sine squared z plus cos squared z and differentiate it, and let's see what happens. So we apply the chain rule to this thing, and we get sine z cos z. And we apply the chain rule to this thing, and we get cos z. Well, I guess there's a factor of 2 here. I'm just anticipating that it's all going to be 0. So 2 sine z times cos z, and then here 2 cos z times negative sine z, and everything cancels and gives us 0. So this is going to be important in our later proof here. Not only do we get that sine squared z plus cos squared z has a derivative of 0, we get it purely from these derivative interchange properties of sine and cosine. And so if we have any other function that obeys similar derivative properties, then we can immediately conclude that it will also have this Pythagorean property. Now, I haven't proven that sine squared plus cos squared is equal to 1, which is the familiar Pythagorean identity. Well, that comes as a consequence of the special values of sine and cosine. So at z, so at z equals 0, and this should be written cos z and sine z. So at z equals 0, these things are easy to calculate. In fact, that's the only value of z at which these are easy to calculate. But we just pick off the constant terms. So cosine of 0 is 1, and sine of 0 is 0. And so that gives us these special values. And if we have these special values at 0, then that tells us that we can calculate this constant by evaluating this function sine squared plus cos squared at 0. And so when we evaluate it at 0, we get 0 squared plus 1 squared, so it's 1. So it must be constantly 1. It must be 1 for all values of z. So that's the argument for 4b. Now, okay, so that's the Pythagorean identity, and it follows from this. So basically, there are only 2 things that we really needed to prove here. The derivative interchange properties here, and the values at 0 here. And now we're going to say if we had any other function, any other 2 functions, s and c, sort of like an alternate sine and an alternate cosine, if we had any other pair of functions, s and z, with these equivalent derivative interchange properties, and these equivalent special values, well then they must be the functions sine and cosine. So the s and c here really stand in for whatever functions you believed in before complex analysis from your trigonometry course or your calculus course, whatever functions you have been calling sine and cosine in the past, but are skeptical that they might not be equal to these power series functions. This is basically assuring you that those functions really must be equal to those power series functions. Now, the functions you knew in the past were probably real valued, and so when we deal with this uniqueness proof, we'll consider what if these functions are only defined on the real line and they have real values. What if these functions are defined on the entire complex plane? So that establishes 4. Let's try to deal with the uniqueness claims in 5. This proof here that this proof that sine squared z plus cos squared z is constant depends only on the derivative interchange properties. And so in 5a, the first thing we can do is we can deduce a derivative interchange property implies the constancy of this thing. So 5a, well, let's just begin 5. Assume a and b. So then s squared z plus c squared z is equal to 1 for exactly the same reasons as we were able to prove that in part 4. Moreover, what we're going to do is we're going to also prove a similar property for these functions which are the difference functions between sine and cosine. If you want to show the 2 functions are equal, then it's natural to subtract them and prove that the difference is 0. So what we're going to do is we're going to let sigma be basically the error in the sine function, the difference between my sine function and your sine function, and let's let gamma be the error in the cosine functions, the difference between my cosine function and your cosine function. And now what we notice right off the bat here is that the derivative of sine is cosine, and the derivative of s is c, and so the derivative of sigma is gamma. So, so sigma prime is equal to gamma. And moreover, the derivative of cosine is minus sine, and the derivative of c is minus s. And so that means that the derivative of gamma is minus sigma. And these are really the derivative interchange properties that we showed above. They apply not only to sine and s by assumption, but also to the error, the difference between those two functions. So this is the derivative interchange property that we proved in 4. And the reason I deduced the Pythagorean constancy property from the derivative interchange properties was because now we know that we can apply that same proof to sigma squared and gamma squared. So what do we deduce from this? Sigma squared of z plus gamma squared of z is constant. Now, I'd like to say that it obeys the Pythagorean identity, but that's not exactly true, because the constant that it's equal to is not 1 anymore, right? So we can prove that it's constant in exactly the same way we established for A, but it's not constantly 1, because sigma of 0 is 0, and gamma of 0 is 0, because the errors of these functions are 0 at the origin. Why? Because sine of 0 is 0 and s of 0 is 0, so the difference between them is 0. Cosine of 0 is 1, c of 0 is 1, so the difference between them is 0. So these things are both 0 at the origin. And so what we get is that sigma squared of z plus gamma squared of z is constantly equal to 0. It's equal to 0 for all z. And now, here's where this becomes a choose-your-own-adventure proof. If we wanted to do our analysis for real-valued functions of a real variable, then at this stage we would be essentially finished. Because we have the sum of two squares equals 0. And squares have to be non-negative, and if the sum of two squares is 0, then they must each of them be 0. So here, let me write this in a different color. So if sigma and gamma are real-valued functions of a real variable, then sigma and gamma are both the identically 0 function, and s equals sine, and c equals cosine, and we're done. So, okay, that's nice. But why am I saying if? Because this is a complex analysis course. And now, so this isn't the only possibility. This does deal with our situation. I mean, this does solve the problem if your prior knowledge of sine and cosine are real value functions of a real variable. Because here we're comparing the real valued functions of a real variable called s and c, which come from prior knowledge, to the real valued functions of a real variable, which are these things, these power series, but restricted to the real numbers. Notice, of course, that because there are no non-real coefficients here, when we plug in real numbers here, we will get real outcomes. So cosine and sine, defined by this means, are real value functions of a real variable if you simply restrict them to the reals. So if that is the situation that we're in, and if we're only interested in proving that the formerly known sine function and the formerly known cosine function agree with these things on the real numbers, then we're done. However, this actually states something stronger. It states that if we had any functions at all that did this, even over the complex plane, then they would be equal on the complex plane. And this logic that allows us to say that these are both equal to 0 is not valid on the complex plane. It's close, but not quite. So here, squares don't have to be non-negative. They don't even have to be real. And so what we're going to do is we're going to sort of take for granted that we want this stronger feature here, and we're going to continue this proof. So what happens here when sigma and gamma are allowed to take complex values? Well, we still get a pretty strong statement here. We get sigma squared of z is minus gamma squared of z. And so taking square roots of both sides, we get sigma of z equals plus or minus I gamma of z. Now, this means that sigma, but notice, of course, that gamma is the derivative of sigma. And so, so basically, sigma prime of z over sigma of z equals plus or minus I. Now, that's if, well, that's if I can safely divide by sigma on both sides of this. So really what's going on here is I have or sigma of z equals 0. So there are two possibilities, basically. The first possibility is, well, what we will see is actually true, that both of these functions are equal to 0. The second possibility is that they're non-zero. I may divide by one of them, and now the ratio between a function and its derivative is equal to plus or minus I. Those are the only possible two values of the sigma prime of z over sigma of z. It can be positive I or it can be negative I. Now, if sigma of z is non-zero, then, well, if sigma of z is 0, then we're kind of done. And if this is true, then we can prove that it's an exponential function. But the problem is, like, this could be true for some z, and this could be true for other z. So it's not a matter of, like, either for all z, this thing is identically 0, or for all z, this thing is plus or minus I. What we really know from this is for each z individually, either this sigma of z is 0, or it's non-zero, and this ratio is plus or minus I, but it could be plus I for some and minus I for others, which is kind of awful. So what we're going to do is we're going to show that this set of z entailed here is going to be Clopin, and so we're going to eliminate that condition. So let's see how that's going to work. So let's consider, let's assume that for some z, we get this ratio, and it actually works out to be positive I. So let's see what happens when we do this. So suppose, this marker is no good, suppose for some z, in the complex plane, then we get sigma prime of z over sigma, well, I should state it explicitly. Sigma of z is non-zero. Sigma of z naught is non-zero. And sigma prime of z naught over sigma of z naught is equal to I. Now, in a neighborhood of z naught, so in a neighborhood, say a ball of radius epsilon around z naught, in a neighborhood of z naught, then sigma of z naught is non-zero. If it's non-zero at z naught, then it's a continuous function, which it is because it's differentiable. Then it must be non-zero in a neighborhood of z naught. So on a neighborhood, then we also get non-zero. So on that neighborhood, then sigma prime of z, of z over sigma of z is continuous and maps to plus or minus I. And so on that neighborhood, if you have a continuous function and it can only take two values, then it can only take one value. So on that neighborhood, sigma prime of z over sigma of z is positive I. So in other words, if it's positive I at one point, then it's positive I on a neighborhood of that point. Okay, so what? So then on that neighborhood, then we get sigma of z is equal to some constant times e to the I z. Why? Because it's proportional to its own derivative on that neighborhood. And so by the previous proof about the uniqueness of the exponential function, then it must be equal to some constant times e to the I z. Now, I don't know what that constant is, but that's all right. So So now, if we subtract these two functions, then e to the z minus c e to the iz, so sigma of z minus c e to the iz is equal to 0 on that ball. Now, so what this shows is that we have a ball on which this function is going to be equal to 0. Now, but this function that I've written, so this function here is going to be 0 on the interior, on this open ball. But this function that I've written is now a continuous function of z. So this thing is continuous function of z on the entire complex plane, actually, for that fixed value of c. And so this is a continuous function. And so the set of all z, so that sigma of z minus c e to the iz is equal to 0 is closed. So in other words, we kind of get a functional equation where we say there's this particular constant c, and sigma z minus c e to the iz is equal to 0 on some open ball. But that function, the set of all values for which that function is equal to 0 will also be a closed set. So this argument up here shows that for any z for which this is true, sigma prime of z over sigma of z is equal to I, and then this must be the case on some neighborhood. So this prior argument shows that this set is also open. So in other words, if you picked a different z naught, which was in this set, then that would be a z naught for which sigma prime of z naught over sigma of z naught is equal to I. And then we would have, similarly, we could make the same argument, and we would get a neighborhood on which this is true. And so this set is clopen. And so this set is either the entire complex plane or it's the empty set. Now, it can't be the entire complex plane. The reason it can't be the entire complex plane is that sigma of 0 is 0 and gamma of 0 is 0. But c times e to the iz is not 0 unless c equals 0, which it's not in this case. So this set cannot be the entire complex plane because it doesn't have the origin in it. And so this set, therefore, for each c individually, so for each c, this set of, so for which this is equal to 0, this thing is empty. And that means, but I mean, we discovered this set by just assuming that for some c we have this thing is equal to I. And that means that there is no z naught for which this thing is actually indeed equal to I. And so sigma prime of z over sigma of z cannot equal I. And by similar argument, just for a different constant, it also cannot equal minus I. And so there's only one other alternative, and that is that this function is 0. And so sigma of z equals 0, which is what we wanted to show, because that shows that sine of z is equal to s of z. And then, of course, differentiate both sides, and you get cosine of z is equal to gamma, not gamma, but c of z. So this shows that the functions sine and cosine given here obey special laws, a basic differential equation that interchanges their derivatives, and also the special values that they take at the origin. They obey these basic laws, and they are the only functions that do obey these laws. Any other function that obeyed these laws would have these properties, If it's a real value function, you can stop here and eliminate it. If it's a complex value function, you get another alternative which you have to do more work to eliminate. And so for all of these reasons, sine and cosine are the unique solutions to these functions, to these equations. And that proves that if you have some prior knowledge of cosine or some prior knowledge of sine, and you know, for example, that their derivatives satisfy these properties, then you may trust that when real values are plugged in here, we really do produce the same answers, that these, when restricted to real values, are your familiar sine and cosine functions.